Back from after the coffee break. Our next speaker is Vikas Garg. He's from Aalto and he's representing the Finnish Center of Artificial Intelligence. That is a joint venture between Aalto and Helsinki University and covers a lot of machine learning development. And Vikas is working on molecules and specifically generative models for molecules. So the stage is yours.
Thanks so much for having me. So today now we will be covering about some aspects of AI and machine learning, how that could be useful, for example, for generative modeling. Yeah, we can have. Yeah, so
you're pointing it at yourself.
Oh, okay, sorry. I don't think I need it. I'll just like me. So let's begin with what are generative models. So you might have heard a lot about ChatGPT, Midjourney, and like these kinds of models that have really gathered attention over the last year or couple of years, if I may add. So generally, these are machine learning algorithms that could, for example, generate new data of the form that you like. This could be text. For example, ChatGPT is an example of a text-based generative model. It could be your images. So you have a bunch of images, say, of faces of some people, and you might want to generate, for example, more images similar to those. But also, these models can be used for transforming from one form to another. So I could, like, for example, say, I could give you, for example, a caption and then say generate an image, for example, that matches with that caption to a large extent. And so the scope is really broad about like what can be done with these models. Sorry, this is a computer issue. I will have to reshare the slides. Yeah, so there is a lot that you can do, for example, with these kinds of generative models. And so this is the rough agenda that we have for today. We'll first take a very quick look at how the generative models essentially work. So I'll try to give a rather very high level overview of how these models work. Then, because we are talking about, say, generative models for molecules, so we will be largely focusing on graphs. Of course, you could have sequence-based representations, you could have other kinds of representations, but for the purpose of this talk, we will largely be focusing on the graph-based representation. So you are given, for example, some molecule. How would you represent it? How would you encode it in terms of numbers so that you can work with a machine learning algorithm? So that would be the focus of this second part. And then third part, we will then come to how does all of this fit in together? How do we essentially generate, say, molecular graphs? So first part, let's begin with how do generative models work in general. So these are broadly the four main kinds of generative models. So of course, like there are adaptations that you have to do based on the domain that you are dealing with, whether it's images, whether it's text, whether it's molecules. But broadly, these are the main categories of generative models. First is so-called generative adversarial training. Here, the idea is that I give you, so imagine it being a game between, for example, a painter and a real painter and a fake painter. So real painter has their images or say their molecules, and now there is a fake painter who tries to pass on. Closer to this, okay. Yeah, so there is, let's say that there is a game between the um, real painter and say like a fake painter. Fake painter tries to pass off as the real painter, like the way they sketch. So let's say that there is a game between the two. So over a period of time, if you get some kind of feedback saying that whether this image looks like being that of the true painter, and if there's, then the two get better at each other. I mean, the system gets better at identifying which are the false paintings, which are the fake paintings, which are the true paintings, and likewise. So this is the generative adversarial networks. The second one is what is called the variational autoencoders. Here, the idea is you have X as your input. So let's say that this is a molecular graph. And what you are trying to do is you have a parameterized model. So these are some variables whose values you are trying to ascertain or like estimate based on the data that is available to you. I give you a bunch of molecules. So you're trying to encode using this encoder. You get a latent representation. We'll go into how, for example, you represent how this encoder works in the second part of the talk. But suffices to say that you get a bunch of numbers that you can then work with. And then you have what is called a decoder. The idea of decoder would be to convert back from the numbers to the original space. Like, for example, that would be your molecules or molecule-like structures. So one of the issues with these variational autoencoders is that while they are very interpretable, they are very well understood models to a large extent. Because your encoder is essentially doing some kind of low dimensional mapping, so you lose a bit of information. So you have a high dimensional molecule, molecular graph. If you concatenate, for example, the features of the atoms together and put in the bond information. So you have a high dimensional structure, but now you are encoding it in a significantly lower dimensional space, and hence you will necessarily lose some information. So flow-based models, which are these normalizing flow methods, for example, they take care of this issue. So you essentially your encoder is of the same dimensionality as your input representation, whatever input you have, and then you essentially do a series of invertible transformations. So you could take, for example, your molecule, um, you know, uh, take it to some other distribution, something which is tractable, say, for example, Gaussian distribution from which we know how to sample, and then you can follow the reverse path. And then the final class, which we would be talking a lot about today, which is the diffusion model. So these are the state of the art now in generative modeling. Here, the idea is again that you take some object and you progressively add uh, small noise to it. So you start with the original data, you have some data distribution, you have samples from the data distribution, and then you add some more noise, so you have perturbed that distribution. And if you keep on slowly adding small noise to it, ultimately you'll end up with say a Gaussian distribution, a fully noisy distribution, which essentially means that at this point you've lost all the information about what was your starting molecule, or X in this case. And then the reverse path again is now denoising. So you will again have multiple steps. At each step, you'll try to guess where did you arrive from. So you'll try to remove some noise, again remove some noise until you reconstructed something which seems very close to a molecule. And so how does this work? So for example, if you want to generate, let's say that you've trained this model with the data that you have, now you can just sample from the noise, because you essentially found a mapping between your say molecules and this latent space or the Gaussian distribution, for example. So you could sample something from this Gaussian distribution and just follow the reverse path, and then you would construct hopefully something which resembles molecules. So I hope like this is broadly clear. There are also other kinds of approaches where you try to build in, if there are more complex processes, you could build in physical simulators. And the idea would be someone gives you a data set and you're trying to readjust the parameters of these simulators until they seem to roughly align with the data that you are given. But so we will not be talking about simulator-based approaches here. Okay, so then the next question is, how do we actually encode molecular graphs? Because in order to be working with any machine learning or AI algorithm, what we want to be able to do is to assign, say, a d-dimensional representation for each graph. We want to be associating a bunch of numbers so that, and our idea essentially would be that different graphs pertaining to these different molecules, they map to different points in the space. And we would, of course, hope that points that are nearby, they pertain to molecules that are similar in some sense. So we need to find a representation here for each molecular graph that we have. And just to say like how we can represent, I mean, the first question is how do you actually represent molecules as graphs? So you could, for example, think of these nodes and the edges. So edges would be your bonds. Nodes would be like, for example, your atoms in this case. And similarly, this can be extended also to like, for example, polypeptides and all, just the dictionary, changes. And then you see all these different kinds of structures. For example, you would have these cycles or rings. And so there are multiple ways to handle these kinds of structures. So you can not only encode, for example, the atoms, but you could also take, find meaningful encodings for these rings and loop paths, and then you get an overall representation for the entire molecule by stitching together essentially these individual representations. When it comes to encoding graphs, the so-called graph neural networks or GNNs are the state-of-the-art models. So there would be different, seemingly different architectures, but largely most of them are inspired by GNNs in one way or the other. And the essential idea is very simple. So what you try to do is, so think of the nodes. So you have nodes in the graphs. This could be, say, a carbon atom at a particular location. What you are trying to do, you start with some representation of carbon. So this could be, for example, the boiling point or like some other kinds of features that you have for the carbon atom. And you repeatedly exchange information with your neighbors. So covalent bonds, here we are talking about information being shared along, say, the covalent bonds. So you know for each node what's its neighborhood, and you share information between the different neighbors. So each neighbor gives each neighbor shares its current embedding or with the with and you keep on doing this. And there is a learnable transformation at each step. So you're applying, for example, the same kind of linear transformation. Each takes this information from all its neighbors, it tries to aggregate or put it together, this transformation, and then it becomes its next embedding. And then you again keep on doing this procedure. So the important thing being that while you start very locally, because you're only exchanging information with your neighbors, over a period of time you will have a more global perspective, because now your neighbors themselves would have gathered information from their neighbors and so on. So just to make it more concrete, let's just take this toy example. You have, for example, a 5-node graph here. And let's consider a 2-layer graph neural network. So initially you see the input layer, just the features. So this could be, for example, A could be carbon. I mean, this is clearly not a molecular graph, but so you have the features of the different nodes. So you have features for A, B, C, E, and D. And so this is your input layer. And then after the first layer, you get a representation for the different nodes. So in this case, for example, node B has neighbors C and A, C has neighbors A, B, and E. So this happens for every node. Every node aggregates information from all its neighbors. And then you again have another layer, because it's a 2-layer graph neural network, where node A aggregates information, for example, from its neighbors. So you would have these kinds of, say, trees. You would have 5 trees for this. So I have shown only for A, but similarly you would have trees for B, for C, for D, and for E. And so at the end of it, what you see here as H2, this is essentially the final embedding that you have for node A. And then once you have these individual embeddings for all the nodes, then you can concatenate them together. You can take their average. You can apply another transformation to get a single representation for the entire graph. So modulo some changes, your minor edits, you could essentially apply this procedure to even get an embedding for any molecule. Yeah, and so this can be essentially, this whole procedure can be summarized in terms of a computation tree. I am interested, for example, in embedding of node A at time t equal to 2. This embedding of node A depends on its neighbors, their embeddings from previous time steps. A has 3 neighbors here, B, C, D. So you take their embeddings from previous steps. In turn, their embeddings depend on their neighbors from the previous step, which in this case happens to be time t equal to 0. So I hope this, at least the broad idea is conveyed. Okay, so now we come to the core of this talk, which is how do we design then generative models for graphs. So what do we mean by that? We have a bunch of molecules. Let's say we abstracted them in terms of molecular graphs. We've trained a machine learning model, a generative model for that purpose. And now I want our model to be, suggesting new molecules. So that's the goal. So usually when we talk about molecules, I mean, whether it is for materials or it's for purpose, like for example, drug discovery, the space that we deal with is really huge. We are really talking about, like a combinatorial space. This is a massive space, and we have to search for example, structures that are meaningful. And so it's a hard problem, and this problem, of course, gets even worse when you talk about these polypeptides, and like you could have, like for example, proteins ranging over, say, thousands of residuals or amino acids. So you could really have a very very challenging problem. It's not an easy problem to solve. That's what I'm trying to convey here. And one of the issues that, for example, models like that used to face about 3-4 years ago was that they would spit out some structures, but they would not even be chemically valid. So you would violate, for example, the valency of carbon atoms in some of the carbon atoms in your molecule, and so on. So it actually took some time to take care of this issue. Second thing, which also was a bit of a concern. Usually, we are not just interested in, for example, generating new molecules. What we are interested in is in some kind of controlled generation. What that means is, I have a bunch of desired properties, durability, or and you have, like, say, for example, rough ballpark numbers for what you want for each of these properties. And what you would like to do is to generate molecule that roughly satisfies those properties. And so this is also something that we'll look into in a bit. And so, like, just to recap, I hope that you remember this picture. We'll be talking largely about the flow-based models, which apply invertible transformations, and then also diffusion models, where we progressively add noise and then try to denoise in multiple steps. So it's easier to think of flows or the normalizing flows when it's just a single object. So for example, if you have an image, you can just set up a flow on the image. It's not immediately clear how do you deal with, for example, more complex objects such as molecules. And so one way to do this is to think of some kind of modular structure within the molecule. So what you could do, for example, is take any molecular graph. I could take the rings, replace them with some other token. It's like I know that there is carbon, there is oxygen. I could pretend that this ring that is there, that's appearing, I could also replace it with some new token, ring token. So I could always represent a molecular graph in a tree-based representation without any loss of generality, because I would just replace, instead of generating now carbon, oxygen, nitrogen, I would also generate in addition these ring-like tokens. And so one way to proceed from here is that we associate a flow with each of the individual nodes that you have in this tree representation. So you say, I will try to, for example, if it were a diffusion model, you would say, I have some information about this node. I'll try to progressively add more noise to destroy this information, and then I'll try to reconstruct this node. And so when it comes to, for example, using flow-based models where you are doing invertible transformations, one could start from, with each node you associate a flow, and then you apply a bunch of invertible transformations. But you don't want to just do invertible transformations on the node itself. You also want to share information from its neighborhood. Otherwise, you would be left with multiple independent flows, and that does not really serve the purpose. So the idea would be to aggregate information from your neighbor. So if you look at this equation at the bottom, and I promise there won't be too many equations here. We are trying to track the evolution of each node. So each node started with its embedding. So carbon started with its embedding, a ring started with its embedding. We started with this. And then over a period of time, each node is aggregating information from itself and those of its neighbors. And this is what you F theta that you see here. This is a model. This could be a graph neural network. This could be some variant of graph neural network. And over a period of time, these flows get intertwined because now you are sharing information with your neighbors as you take multiple steps. So you become increasingly more aware of your neighbors and their neighbors and so on. And then once you have this, you can essentially destroy information in a collective way and then try to reproduce your original structure. And so that's how these models work. And so this has been a while because this work was like 2 or 3 years ago, but it really enhanced the validity that you got. For example, the chemically valid structures that you would generate, new structures. There are other kinds of things that you care about, which is diversity, novelty. So you don't want to be just generating something that was already given to you as part of your training set. And so it, over a whole bunch of metrics, it does quite well. Another way, for example, to what you also want is to do some kind of property-based assessment. So you have these different properties, and you want to see once you've generated these molecules, how close are they to the actual training molecules that you were given? So someone gave you some data, and now you're generating some new data. So you're trying to see whether, on a per property basis, are you having something similar or different. So you would like these to be very closely aligned. And then you could also do some kind of property targeted optimization. You've trained a model, then you start with some input molecule, and now you say, for example, hey, can you generate me something which is better? So I want the core structure to be more or less similar, but I want to enhance, for example, some property, or I want to suppress some other property. So then you could also do these kinds of things with these models. Now, one of the things, as I mentioned, which we care about is controlled generation. What does that mean? So I might want to just enhance or suppress a bunch of properties without affecting the others. So it's not always possible, because there could be some properties that are very highly correlated or that have a tight coupling between them. But to the extent possible, you would want this kind of segregation. In some sense, you would say, hey, I only want to enhance, for example, durability. I don't care about the rest of this, or I want to reduce, for example, some brittleness and so on. So how would you achieve that in a generative model? So this is another question that arises quite naturally when we talk about generative models for molecules. And so So here is a motivating example. You have a bunch of images of objects. These objects have say shape, size, and color. And what you want to say is, I only want to change the color. I want to keep the ball as is. I just want to change, for example, the color. And so similarly, one could think of in terms of molecules. I want to retain the essence of the molecule. I don't want to affect the other properties, but for some properties, I would like to do better. Um, and so the first one way to do this is to do some kind of unsupervised property disentanglement. So the idea would be that I have this molecule. I've represented it, for example, as a graph. I use the encoder as before, which is, say, for example, a graph neural network. I get some representation, which is the latent representation. So I get a vector for a for a molecule. And now what I will try to do is to segregate this latent space. So think of it, you have a d-dimensional space. You would say, let's say that there are k properties. You would want to assign only a subspace to each property. And so you would only, if you are able to do that successfully, now you could only change some information, for example, in that particular part, leaving the rest of it intact. And that would allow you, for example, to be able to control what you generate. And so this is, for example, one way. But here, I guess like one of the downsides is you don't know the property beforehand. No one is telling you that this part of the latent space pertains to some actual physical property like durability or not. So we'll see how that can be done. But you can formulate very nice, very easy to train models. So these are, really easy. You can just train these models on your laptop, and it's really easy to train some of these models. And here is an illustration, for example, how these models are supposed to work. So you take, for example, some different kinds of graphs, and then if you change along one axis, which is a part of the latent space, you would only change the size, or you would change the density, for example, on the other axis, or you will change the connectivity. So this allows you, for example, to control these kinds of properties in a very, very natural way. And again, it significantly leads to improvement in the performance, even when it comes to different kinds of standard metrics that are there. Now the question is, in real world, as I said, we really care about controlling the properties. We know what are the properties of interest, and we would really like to generate something that is aligned with these desired properties and their ranges. And so in one of the things which we call diffusion tricks, the idea would be you build this kind of control as part of your model itself. So as I mentioned, that we could represent these molecules as graphs. These are the graph structures. So you could think of multiple processes. You could associate, for example, one diffusion process with the structure. And now you say, conditioned on this structure, I would guide the rest of the properties that are there. So, structure is more like an independent property. And then you would like to, for example, regulate the flow of information between the different properties. And you could set up very similar system in like where you incorporate information between the different properties via the structure. You could set up these kind of stochastic differential equations, and again you could train these models. However, these models are really very slow to train. They take lots of compute power. That's their downside. And then you could, for example, generate, these are very, as you can see, like essentially the whole algorithm, or at least the key steps are just like a few lines of code. So these are very easy to code up and work with. And these are here I'm showing comparisons, for example, with respect to the quantum mechanics QM9 data set, and you see here with respect to lots of quantum properties, how this model performs much better. And you could, in fact, like I have not shown the results here. You could also vary multiple properties at a time. You could specify what you care about. Similarly, for example, one of the things, if you are talking about, for example, molecules for pharma, then in that case, you would typically have a protein target, and now you would like to generate something that would fit into that protein target. And so you're looking for these docking scores. So this is other bit of information that you would like to condition on rather than just properties of the molecule itself. And again, so this kind of captures the interaction between say two objects that you are generating. And again, you get a whole bunch of improvements in the results. So I would not go into the details, but for example, you could condition on some specific properties, and you could generate molecules that are known to be very close in those properties. So there are lots and lots of questions here. This is just a beginning from an AI perspective, because one of the issues is you typically, because of data scarcity, as I said, this is a huge space, and our data sets are pretty much never going to suffice. So we tend to exploit the symmetries in the data. So through equivariances, through invariances, and all. But then they come with their own drawbacks. And like, for example, one of the drawbacks is when it comes to stereochemistry, you have these different kinds of stereoisomers, and then you are not able to differentiate with these equivariant models. And so there are representations, there are more elaborate representations that can help you circumvent these kinds of issues. So you actually treat different conformations of the same molecule differently. I mean, that would be the idea. There are other applications also when it comes to generative models for molecules, because you can now talk about retrosynthesis or synthesis planning. Given a target molecule, let's say that you want to actually synthesize in lab a target molecule, so you will need to carry out some, say, chemical reactions. How would you do that? So AI could also actually help you expedite this process significantly. So you would actually say, what should be the initial starting material that you should be starting with, and then what sequence or chains of reactions you need to carry out to achieve the desired molecule. Sorry, I need to stop once more. Yeah, so you could also do some kind of inpainting. For example, I give you a product, and then I also specify, say, one of the starting material, one of the reactants, for example. And then you say, could you find me the other one? So you could do all kinds of questions you could ask in this setup. Yeah, so I'll just conclude. So there are lots of very interesting problems, and these are rather challenging. But ML has shown huge potential and promise recently. The area is very interdisciplinary. It uses lots of very cool math, and then also like knowledge about material science, about molecules in general, synthetic chemistry. And so there are lots of very interesting problems to be solved in this domain. And typically the advances hinge on, for example, realizing what is being modeled by the existing architectures, what is not being modeled, what are the shortcomings of the materials that or the molecule processing that you are doing right now, and how could you, for example, improve upon this. Yeah, and I would leave with a bunch of publications if you want to take a look. So these also engulf, like, for example, polypeptides, proteins, and so if you different kinds of macromolecules, and so you could take a look at these if you are interested. Yeah, and I'm ready for any questions if you may have.
Thank you, Vikas. Other questions? So Emma.
Thank you, Vikas. That was a really lovely talk. I'm definitely going to have to check out your molecule flow afterwards. That was very interesting. I actually have two questions, and they're somewhat related. So I noticed in the beginning of your talk, you had some really beautiful pharmaceutically relevant molecules that had stereocenters, stereogenic centers. And then partway through, when you started talking about generation of molecules, you'd lost those stereocenters. Could you comment a bit on if your generative models can handle stereogenic information? How is that dealt with? And if not, what are the future plans with that?
Yeah, so for example, I mentioned about this chirality, right? I mean that you could handle the stereoisomers. This essentially the idea would be, so these were all, I will just give you like an example. So the idea would be you could resort to field-based molecular generation. The problem with symmetries is that you don't know how to break the ties. I mean that the issue would be, for
Sorry,
example,
you don't break the tines?
yes, so you have, for example, two conformations, and now you do E3 equivariance, as I said. So E3 equivariance is permutation, reflection, translation, and rotation. And so if you impose on your model, which is in terms of your GNN layers that I said. So you could make, for example, your GNN layers equivariant to these specific operations like rotation, reflection, and then you would not be able to differentiate between, for example, these two stereoisomers. But the way to, for example, take care of these and like other kinds of asymmetries, for example, asymmetric conformers, would be that you could think of essentially a d-dimensional representation where you directly work with the fields. So let's say that if I associate a mixture of Gaussians for the for each of the nodes that you have. Now, because depending on the locations of the other atoms that are there, the intensity that you would have, or the distribution, or the mass that you would have at any single point would differ across, for example, this field that you would have. And then when you map, for example, these different stereoisomers, then they would be mapped to different locations, and hence you are able to differentiate. You could also, I did not go into details of retrosynthesis, but there also you could model this information, like, for example, what are the reaction centers and where does the reaction happen, and you can also do some kind of atom mapping between the product and the reactants. So there are lots of things that you have to do on top of what I mentioned here. But hopefully, like once you go and take a look, you'll find some information useful.
Yeah, thank you. Because I know I sort of a bit of a comment on the retrosynthesis, right? The big part of retrosynthesis, that's the challenge, is stereo control, right? So if you have a reaction that can give you two stereoisomers and one that can give you one stereoisomer, right? You're likely going to choose that selective reaction.
Yes.
My second question was based
And
on.
so you could do, like, for example, so this was, I showed here only for single step. Generally, you don't do single step. Generally, you have a synthesis plan. So you essentially search over a sequence of reactions, and you could specify then essentially a cost, for example, with each reaction. So you could assign lower cost to the favorable reactions compared to, for example, the not so favorable things. And then you could bias your model towards generating, for example, stereoisomer of one type over another.
Yeah, that's thank you for that. My second question had to do with the ring tokenization. I was wondering if you could discuss that in a little more detail, or maybe I missed exactly how you were differentiating between different types of rings.
Yes, so you would essentially take the different kinds of rings. So you only care about the most frequent rings, because that helps in learning. If a ring does not appear prominently, it's only appearing in one or two molecules. Anyway, the model would overlook it because there is so much data that it is kind of averaging over. But what you could do, for example, is, let's say that you have like a usual vocabulary of four, say carbon, hydrogen, oxygen, nitrogen. Say, let's put in sulfur also there. So you have, like, say five of these atoms. Now, what you would also find out is some of these most frequent rings that you have, and there would be different rings would be assigned different tokens. But now I take a ring that appears quite frequently across, for example, many molecules. So I would assign a separate token for this ring. And so now I would have an extended vocabulary, the 5 base, carbon, hydrogen, all these, plus these different ring tokens that I have. And so now I could essentially think of aggregating information over over their respective neighborhoods.
I see. Okay. And does that include substituent information as well on the rings or fused rings or bridged rings?
Yes, you could. So you could, for example, you could take these fused or these conjoined rings. You could model. I mean, these are very flexible, like, because it depends on how do you tokenize. That's entirely up to you. Of course, you want to be, to exercise some kind of discretion in how you tokenize. You don't want to tokenize every ring, because if it's just appearing once in a while, it will only add to noise. It's not a frequently occurring pattern or structure across your molecules anyway. But at the same time, if something appears quite frequently, you have the flexibility to be able to assign a separate token to it.
Okay,
Yes.
one more question over there.
Hello. Thank you for your inspiring speech. Actually, I have some questions about your architectures. Firstly, it is about the because you claim you use the three-dimensional neural networks for extracting the molecular information, but I didn't see what kind of features you use to represent the atoms or the edges. So this is my first question, and the second one is actually how because you mentioned you divided or distributed the latent space in the the generative model for different properties, but I wonder sometimes when we're doing the modeling, I'm sorry. Sometimes when we're doing the QSPR modeling, we will face some entangled properties, say by toxicity to aquatic creatures and mammals, and or like chronic or acute toxicity. So when in this case, how can you properly divide the latent space for different properties? Yeah, thank you.
Thanks. These are again like great questions. So coming to the first part, how do you, for example, represent? What are the kinds of features you use? So if you were to only take, for example, structure into account, then the one way would be, so let's say that as I said, that let's consider only oxygen, nitrogen, carbon, hydrogen. So you have like, say, four atoms in your molecule. So for each node, you could do a one hot vector representation. So if it's a carbon atom, say the first position is for carbon, second position is for oxygen, third position is for nitrogen, fourth is for hydrogen. So I could just put a 1 to denote the carbon node and zeros elsewhere. This captures the structural information that I know that this is a one token, which is carbon. Likewise, if it were oxygen, then I would use probably the second or the third index and set the rest of like others to be zeros. But you could also augment the properties that you know about that particular atom. For example, as I said, boiling point, atomic number, and atomic mass, and like these kinds of properties that you really care about, those can be concatenated to this one hot vector representation that I said. This was for the node bit, but you also, of course, need to encode the edges or the covalent bonds. Again, you could use a one hot vector representation to indicate single bond, double bond, triple bond, or no bond. So again, you have this. So this is how you actually represent information. Then coming to the second question, which I think like is really a very nice question. Maybe I could go back and show you the architecture itself. You are right. And as I started by saying that it's not always possible to completely disentangle or separate these properties. This is an issue. And so what you kind of do, if you see in this figure, there is something called the conditional disentanglement. And so the idea would be you first got a representation. Think of your latent space that you have as being segregated. Suppose there are k properties. So you should think of it being segregated into k plus 1 parts. So k parts are, say, like for each property separately. K plus 1 is to capture these dependencies that you could not segregate. And so you actually model that also very explicitly as part of your latent space. And then you see a feed forward connection, like which is labeled conditional disentanglement here, that retains that information and carries it over. So you don't actually lose that information. And so you could actually handle, for example, some of these properties that could not be separated and were entangled. I hope that answers your question. Yeah.
Okay, so I would suggest to defer any further discussions to the